Thank you very much, Delphine, for the introduction. Thanks for the invitation. So maybe before I start, how long is the talk precisely? 60 minutes. Okay. So brief announcement before I start with the math. There will be a conference in Budapest in June this year. It's the 60th anniversary of András Stipschitz and Zoltán Szabó. The conference is not their birthday conference because they specified it. So it's there. We already have a website. You cannot register yet, but hopefully soon. Okay, so now I will get to the mathematics. What I'm going to tell you about is a joint work with Marco Golla, and since I am the first talk on Monday morning, I will start with a boring question to motivate you better. And the question is, what surfaces split a given link in S3. So if you consider a split link, this is a link that is split by an S2 embedded in S3, so this is the classical notion. And what I'm asking is, what happens if I consider other surfaces? And I claim that it's a boring question, because every link with at least two components is split by a torus. Just take a neighborhood of a component and its boundary. You may ask, what happens if you require that the torus is embedded in a standard way? Then you get something that is a little more interesting, but even so, not so much. The other case is when the surface is non-orientable. So if you have a non-orientable surface, well, then you cannot embed it in S3, and so there is no question there. So orientable, non-orientable cannot be embedded. However, the question becomes more interesting if you go to higher dimension. So the real motivating question, not as boring as this one, is the following one that was asked by Kronheimer at a conference a couple of years ago in Oxford. Is there a link in S4 that is split by an integer homology sphere? This is my notation for a three-manifold with the same integer homology as S3. But not by the standard S3. So it's something that is not split by S3, but something that looks like S3. At least on the homology, it's essentially S3. And before I write the main theorem, question, can you read my handwriting and is it big enough? Okay, complain if it becomes smaller. Da-da-da. So theorem. For every n at least 3, there exists a link in Sn plus 1 split by an integer homology n sphere, but not by the standard Sn. So the answer is yes, and it holds in any dimension at least 3. Where do I put the remark? I'll just put it here. So a little remark, there are other manifolds that look like Sn. For example, you may ask, okay, integer homology sphere looks like an SN, but we have something that looks even more like an SN, not being an SN, and I'm talking about homotopy spheres. But you cannot strengthen the theorem to homotopy spheres for two reasons. The first one is that if n is different from 4, then if you have an embedding of a homotopy sphere, let's say sigma n inside Sn plus 1, that splits a link, but let's forget about the link for now. Then you have an H-cobordism from sigma n to an Sn that you obtain by removing a small ball from one of the two components in which Sn plus 1 minus sigma n is split. So you get an H-cobordism from sigma n to Sn, but when n is at least 5, then the H-cobordism theorem tells you that sigma n is diffeomorphic to Sn. So it wasn't anything different. So this reasoning clearly fails in dimension 4. However, in dimension 4 there is something interesting. I didn't know about it actually. And that's the fact that L is split by a homotopy 4 sphere, sigma 4, if and only if L is split by the standard sphere. And the reason is that every neighborhood of an embedded sigma 4 in S5, or really in any orientable, or actually you don't even need orientable 5 manifold, contains every other sigma 4 tilde. So every other homotopy 4 sphere has a homological section. The reason has to do with the uniqueness of the H-cobordism between a homotopy 4 sphere and another homotopy 4 sphere. Okay, so this was the picture of the motivation. I prepared something about some background. I think that for this audience it will be all known, so I will go rather quick on it, but ask questions if there's something that isn't clear. So one tool that we will use are open book decompositions. An open book decomposition of an n plus 1 manifold X consists of an n minus 1, or if you prefer codimension 2 submanifold B, that is called the binding. Tell me.
So just in the statement, so this Sn, are you saying it has the equatorial Sn, or are you allowing any other Sn that might be somehow, I don't know how, embedded into Sn plus 1?
No, I mean, it can be anything.
N-bound the ball on both sides?
Yes, yeah, I see. I'm trying to think, I don't think we use it.
So
No,
just saying
no, it can.
Submanifold which
It's any Sn. It may not bound the ball. Yes.
But which is somehow
Yes.
homomorphic to Sn.
Yes. Yes.
That's what the statement says.
Yes. But No. The link is in SM plus 1.
No,
That's later. No, he's asking about this.
When you say not by SN, what does it mean? It means
Any embedding of SN in SM
any
plus
embedding
1.
of SN in SN plus 1. Okay, thank you.
Oh, but you know, if you have an embedding of Sn in Sn plus 1 and you are at least in dimension 5, okay, I guess in dimension 4 you don't know what happens. That's the problem, right?
Well, I don't know. I'm just want to make sure I'm.
Yes, yes. Okay, we were here. So, yes, open book decompositions. We're given an n plus 1 dimensional manifold X. There's a codimension to submanifold called the binding. And we require that its normal bundle is trivial. And then we are also given a fibration of the complement of the binding in such a way that near the binding it looks exactly like the angular coordinate. And any fiber of this fibration is called the page. So I have a picture here of an example. This is the standard open book decomposition of Sn plus 1. Here n is equal to 1 in the picture. You have an equatorial Sn minus, well, the intersection of two equatorial Sns, which is an Sn minus 1. And we fix it as the binding. And then we have a fibration of the complement that you can see here in terms of longitudes. And each page is diffeomorphic to a Bn. So I will often denote it by Bn theta. And so this is pictured in dimension 2, but it works also in higher dimensions. So far, so good. Everyone was familiar with it. Okay. So now, next notion. So the next notion is the construction of span knots. This was due to Artin, 1925, if I remember right, but I didn't write it up. So you start with a tangle T in the n ball. So here is an example, for example, of a tangle with a certain closure that is a knot K in Sn. And we consider the standard open book decomposition of Sn plus 1, that was the one up there, and we know that the pages are all Bn's. And now in each of the page, I take a copy of the tangle. So here you have the various figures. It's always the same tangle, Tk, here, here, and here. And so I'm spinning around the tangle, and I'm sort of constructing a surface of a rotation surface. And what you get, you can check the Euler characteristic if you prefer, or any other way, is if you start with a tangle whose closure is a knot, in this way you obtain an S2 embedded in S4, and then if you go higher, you get a codimension 2 sphere embedded in Sn plus 1. There is a variation of this construction due to Zeeman, the 60s, where instead of taking exactly the same tangle in every page, you take the same tangle, but you add a rotation. And you add a rotation in such a way that after you go all around the S1 fibration, you get the same tangle again. So for example, here I'm starting with a tangle, and I don't know how visible it is, but I was trying to convey that here the rotation at each step is exactly the angle that labels the page. 2 pi. And if you rotate by 2 pi, you get exactly the picture you started with, so everything is coherent and we get a surface, a well-defined surface again. So some names, where is that? T3. The knot that we get on the left is called the zero twist span knot over K, and this is a knot inside Sn plus 1. On the right, instead we get something that we call SPK of K, where the lowercase k indicates the number of twists that I add, and this is also not inside Sn plus 1. So the variation is that instead of rotating by theta, each page, the page Bn theta, you rotate it by k times theta. Okay, so far so good? Fantastic. So, how should I do that? Let's do this. And can everyone still read? Okay. Great. So we're done. So the fundamental result about twist span knots that we are going to use is the following. Theorem of Zeeman, that is that the one twist span knot over a knot K is always unknotted. Or if you prefer, it bounds an n-dimensional ball. This follows from a more general result of Zeeman that, well, maybe I'll just state the general one too, just to give context. That is that there exists a vibration of the complement of the k-twist span knot in Sn plus 1 over S1, where the fiber is F, with the following properties. F is diffeomorphic to sigma k of k, and this is the k-fold cyclic cover over the knot k minus Bn, k-fold branched over k. And the second condition is that F can be compactified to, and the boundary of F with respect to this compactification is SPK of k. So in other words, there is an analog of the Cypher surface for this knot. You can call it a Cypher hypersurface. That is exactly the k-fold branched cover over k. Now, when k is equal to 1, the k-fold branched cover is exactly a Bn. Well, it's Sn, and if you punctuate, you get Bn. And so this is why the 1 plus or minus 1 twist span knot is unknotted. If you're wondering, in this vibration there is a monodromy map that comes from going around the vibration, and so it gives an automorphism, well, a self-diffeomorphism of this sigma k of k. And if you guessed that it is the generator of the automorphisms of sigma k of k over Sn, then you guessed right. So it's exactly the diffeomorphism that generates the group of deck transformations. So if k is 0, sigma 0, okay, let's say k different from 0. Yeah, sorry. Let's say k is not 0. Yes?
Is there any reason you didn't just say composition?
It's not an open book decomposition. Right, good point. So yes, ideally you would have like a much cleaner statement that would have been there is another open book decomposition of Sn plus 1 with binding SPK, where's that? Here, and with page exactly this. Except that the S1 action that gives you the vibration also acts on what would be the binding. And it's not a free, it's not a fixed, so it doesn't fix what would be the binding, and it's not a free action either. There's a fixed Sn minus 3 here, I think, or 2. 2 probably with this.
It's still true that each fiber, in fact, each fiber
Yes.
union the knot.
Yes, yes. Yes, but it is. It doesn't fix SPKK pointwise. It fixes it as a set, but it moves it. It acts on it. Yes, so it's essentially the same action that you had here, right? SPK is an Sn minus 2, I guess, Sn minus 1, sorry. If you look at it abstractly, and the rotation, the action of S1 looks like this action that fixes a codimension 2 sphere. So there is an Sn minus 3 worth of fixed points, and exactly that. Okay, so now we can go to the construction. Where do I go? I think I want space. Okay. So I'm going to put the statement here on the left, so I will not erase it. This is the main technical ingredient, probably, of the proof. And the statement is that for every knot K in Sn, there exists a two-component link, Lk, associated to it. And this is a link not in Sn, but in one dimension higher. It's in Sn plus 1, such that two properties hold. The first one is that Lk is split by construction by a manifold that I call Yk. This is an n-dimensional manifold. And this is the connected sum of the double-branched cover over K and its mirror. And the second property is that if you take the double-branched cover over Lk, now this one is an n plus 1 dimensional manifold, then this is a mapping torus on this manifold Yk. In other words, sigma 2 of Lk is diffeomorphic to interval cross Yk modulo an equivalence relation that identifies points 0y with 1 h of y for some monodromy h. I'm going to move it up so you all read it. Okay. So that's the statement. And let's see how the construction works. So we need to build a link in Sn plus 1. So I'm going to start with an Sn plus 1. And now in Sn plus 1 we have the standard open book decomposition that presumably I just erased. Yes. So I'll draw a slightly different picture of it. So the binding now will be at the center. So this is just a schematic. It's not a precise picture. So this is Sn minus 1. And I have as an input a knot in Sn. So this gives me a tangle in Bn, and Bn is any of the pages of this open book decomposition. So I construct a knot starting from that, and I take precisely the one twist span knot over K. So let's represent it as something like this. So this is SP1 of K. And now, if you take a page of this open book decomposition, then what you see in here is the tangle Tk. So the tangle really goes to the Sn minus 1 as well, but it's a schematic, so you don't see it. So this is Tk. Great. So now I take the double branched cover over this knot SP1 of K. And that's boring because from the very top board, we know that the one twist span knot is unknotted. If you take the double branched cover over the unknot, you get again Sn plus 1. So I get the same manifold, Sn plus 1. But what is interesting is that I actually get an interesting open book decomposition on it by pulling back the open book decomposition that I have on the right. So I'm going to start with the binding. Recall, we don't see it, but the tangle, this twist span knot intersects the binding, and if you take the double branched cover of that, then you get again an Sn minus 1. And now the pre-image of a page is a page in the new open book decomposition, and this is precisely the double branched cover over the tangle, which is the double branched cover over K, its closure, minus an M ball. So this is the new page. Okay. Now from here, new color, blue. From here, I can construct my link LK. I take the center of the binding of this open book decomposition on the left, and I push off this Sn minus 1 in two directions. Let's say one here and one here that are opposite. So this is going to be my link LK. It consists of two spheres, so that's great, and they are embedded in Sn plus 1. And I claim that by construction this is split by Yk, because here I'm just gluing two pages opposite to each other along Sn minus 1. They are both sigma 2 of k minus bn, but one of them is oriented one way and the other is oriented the other way. And so this is why you actually get Yk as this cut in the middle. So that's great. We got point 1 by construction. Point 2 will be helpful when we will discuss the obstruction. So let's see why we have that. Tell me. LK is obtaining by taking the binding of the open book decomposition, and you push it in two different directions. So you take, say, two pages opposite to each other, and you take a translate of the binding in the two pages, for example. So tuck and tuck. Okay. I couldn't hear to both components. Well, they live in a neighborhood of the binding, but so the binding is an m minus 1 dimensional manifold, so it's like this red point in this picture, and then I take just two push-offs of it. So they live close to the binding. They live in a neighborhood, in a regular neighborhood of the binding. Yeah, yes, I can take two other pages here, and then I take the push-off in those pages. Okay, now the second statement. The second statement is a bit strange, so it's about the double branched cover of this guy over the blue link. So it's another double branched cover that we're taking, so we're building over it. And in order to construct it, you can break this picture in two parts, a neighborhood of the binding and the rest. Let's pretend for a second that n is like very low, something like 1 or 0 or 1 maybe. Or no, a bit more. I'm getting confused, sorry, we have too many dimensions. Sn plus 1. So this is a neighborhood of Sn minus 1 cross d2, so okay. So this is Sn minus 1 cross d2, because the binding has trivial normal bundle. And now if we ignore the n1, the Sn minus 1 factor, because it's a product, then what we are doing is just on the d2 side, and we are taking the double branched cover of a d2 over 2 points. So the double branched cover of a d2 over 2 points is an annulus. And now we reintroduce the S and minus 1 fiber, so what I get is a factor, sorry. So what I get is this as the double branched cover of the central piece. And now on the outside instead, you have that you have a regular double cover of the outside piece, so the complement of a neighborhood of the binding, and it's actually the trivial cover, so it's disconnected. The reason is that if you go around this disk, then you are encompassing both meridians, and so the map that it induces in pi1 of the complement of the link is, h1 of the complement of the link is 0. And so it's this piece union two copies of Sn plus 1 minus a neighborhood of the binding. So now I'm going to try to give you a rough schematic of what is going on. So this is the annulus that we have from here. Well, it's a cylinder, really, more than an annulus. And then we have a copy that is glued inside, and a copy that is glued outside. So the one outside here, we have sigma 2 of k minus bn. As a fiber, it's just a vibration on sigma 2n minus bn. And then the one inside, it's the same, but it's reversed. So it is flipped. So here instead we have sigma 2 of k bar minus bn. And these fibers are glued along their boundary. And so what we get here is that this bit is exactly a yk. So this is the schematic. So what we get is a vibration, and that's the definition of a mapping torus. So we have yk across an interval, and then it's glued somehow. I don't need to know what the gluing map is, but I just need to know that it's a mapping torus. Okay. So now the proof. T1 down. Too much. Oops. Oh, well, okay, just. So now that we have the construction, we just need to show the obstruction part, namely that the link that we constructed now, this LK, is not split by the standard, the Sn. So, proof of theorem. And, well, we also need to show that Y is an integer homology sphere, but that will follow from our choice of K. So, I'm going to do the case n equal to 3 first. So this is the case of a two-dimensional link inside S4. So we start with k in S3, and I choose a non-trivial knot with the determinant of k equal to 1. And there are plenty of these knots. For example, you can choose any PPQ with P and Q both odd. The reason is that sigma 2 of K has first homology whose size is exactly the determinant of K. And so if the determinant of K is 1, then this is indeed an integer homology-free sphere. Moreover, it is not S3 by the Smith conjecture. So different from S3. And so in fact, by Perelman, we have that pi 1 of sigma 2 of K is not trivial. And the abstraction that I will use, we use pi 1. We need to use something more than homology because our sphere is exactly an SN, an S3 from the homology perspective. So one way is to use the homotopy groups. Another way that I will discuss in a little bit is that you can use some TQFTs, for example, Hegel homology. So one way is that you use the fundamental group, for example, something like homotopy theory, or you can use TQFTs, so some smooth methods. So I will say some words about another proof, but using Hegel homology. Okay. Yeah, yes, in this case we can, yes. It's, yeah, I mean, this is the only thing that I need. This is what I'm saying. It was just a shortcut just to convince you of this fact. Okay. I will need that pi 1 is non-trivial for the abstraction.
And it will be enough.
It will be enough. Okay. So now, by the proposition, we have that Lk, that is a link in Sn plus 1, is split by this manifold Yk, that is sigma 2 of K connected sum its mirror. And moreover, we know that, so we know in particular that this is an integer homology sphere with non-trivial pi 1. And we know that sigma 2 of Lk is a mapping torus on Yk. Now, suppose by contradiction that S3 splits Lk as well. Then we can lift S3 to the double-branched cover. So we have this map from S3 to the double-branched cover of Lk, sorry. So S3 is in the complement of Lk, it's simply connected, so we lift it up. But now, sigma 2 of Lk is a mapping torus over Yk. And so here, there's another cover that is R cross Yk. And the condition that S3 splits this tells you that this is a homological section. So when you take a lift, and such a lift always exists because S3 is simply connected, you get that S3 lifts to here, and in fact it lifts as a homological section. By homological section, I mean that the image of S3 lies in the same homology class as any fiber, yk. This follows from the fact that yk split. You can pick a path from one component of the link Lk to the other one. This will intersect the separating sphere once, algebraically. And so this happens also upstairs. And this tells you by duality the homology class of this lift of S3. Okay, so it's just a homological computation. Okay. So the abstraction that we have now has taken form because so this goes up. Which one?
Can you say once more why it did?
It's simply connected. So you can lift you can lift to any cover. So the interesting part is not that it lifts, it's that it lifts as a homological section. So it's the homology class of the image. What again? It means that it is in the same homology class of a fiber. So the picture that you have in mind, should have in mind is the following. This is R cross Y. So here are the YKs. So one down here and one down here. So it's further down. And then this S3 is somehow somewhere in here. So it is embedded in R cross Yk in the same homology class of Yk. So what this gives us, if you see it from this picture, is that we have two cobordisms, one from Yk to S3 and one from S3 to Yk, such that if you compose them, you get the identity cobordism. So this is called an invertible cobordism from Yk to S3, i.e., let's give it a name, W. There exists a W prime, such that W prime composed with W is the identity cobordism over Y, so it's interval cross Y. And this is the key point, because when you have an invertible cobordism, somehow the end manifold of the cobordism is supposed to be more complicated than the one you started with. And this is where we apply our abstraction. For example, you have a degree 1 map from S3 to Yk that is given just by taking the projection down to Yk. And if you have a degree 1 map, this induces a surjective map on the level of pi ones. And this is our contradiction. Okay, if you never saw this before, this is an exercise in covering space theory. So if you have a degree 1 map, then think about covers, and you can prove that it induces a surjective map on the level of pi 1. Okay? So, still have a few minutes. So, note number 1. We did everything with dimension 3 and 4. So how do we go up? Everything still works the same. The only difference is that we have to find a different knot to initialize this whole process. So for general n, general dimension n, you start with the same knot k that you had up there in S3, and you take iterated zero-twisted span knots on it. So you take sp0 of sp0, etc., of sp0 of k. And what you have is that the same point as before still holds here. Yeah, no. This is it. Ah, there it is. Yes. So the double branched cover of this new knot, let's call it J, is an integer homology Sn with non-trivial pi1. So everything works the same as before. And now if I still have a few minutes, I would like to tell you something about a power-up using hierarchical homology. Okay, so here's the theorem. Also with Marco. Suppose that L in S4 is split by an integer homology 3-sphere Y, such that sigma 2 of L is a mapping torus on Y. So we are precisely in the situation that the proposition gives us. Then, if L is split also by an integer homology sphere Z, then HF red of Y is a direct summand of HF red of Z. So this HF red is a graded F of U module, where F is the field with two elements. And it is isomorphic to a direct sum of standard pieces that are F adjoint U modulo U to the di for some di's, and all the di's are positive, or U to the, yes, positive. Okay. And the idea of the proof is exactly the same. You run the same argument as before. So suppose by contradiction that Z splits LK, then you lift Z to the double branched cover of LK, and now it turns out that the manifold that you have up here, well, actually this cover is an abelian cover, meaning that the automorphism group is abelian. And this means that you can lift not only simply connected objects, but every object with H1 equal to 0. So here you have a lift of Z in here, still as a homological section. So the situation is the same as before. You have y, and you want to abstract the existence of a z here. And now you have two cobordisms. So cobordisms in hierarchical homology induce a cobordism map. So you have a cobordism map from HF red of y to HF red of z. And this is an F adjoint U module map. And also it is a degree 0 map. So it preserves this grading. And then you have another map to HF red of y with the same property. But now the composition of the two cobordisms is the identity cobordism. And the induced map by the identity cobordism is the identity map. So we have that the composition of these two maps is the identity. And when you have a picture like that, let's call this map, say, F and G, then exercise the thing in the middle, HF red of Z, splits as what's that, the image of F plus the kernel of G. So this is true over in basically all the categories you can think of. Okay, and so this proves precisely this theorem that HF red of y is a direct summand of HF red of Z. Punchline. Do I have like 1 minute or two to write the punchline? Let's skip this. So as an application of this fact, if you take KL equal to the knot, the torus knot T4L plus 1, 8L plus 3, connected sum with T35, then you get some knots LKL and YKL. And what you have is that for if M is different from N, let's say L positive, then then, okay, let's state it this way, LKL is LKL is split by YKL, but not by YKM for M different from L. So it is split exactly by one manifold of that family. And to prove it, we use this theorem. We just prove that as graded FU to F adjoint U modules, the HF red of the YKLs are never a direct summand of each other. So that's it.